Okay, I think we are live. Okay, welcome everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro Cárdenas Avendaño, and I'm going to be your host. Today, we are presenting Searching for New Particles in the Sky by Masha Baryakhtar. Professor Baryakhtar earned her Bachelor in Physics and Mathematics from Harvard, and then she did her PhD in Physics from Stanford University, where she worked with Professor Savas Domopoulos. Before arriving at the University of Washington, she was a Banting postdoctoral fellow at the Perimeter Institute for Theoretical Physics in Canada, and a James Arthur postdoctoral fellow at the Center for Cosmology and Particle Physics at New York University. She works on a variety of things, and she's going to mention some of them in today's webinar, but in particular, her focus is on theories beyond the standard model and on creating new ideas and direction for testing these theories. We are delighted to have her in our webinar series today. And remember, you can ask questions over email, through our YouTube channel or Twitter, and then the questions will be read at the end of the talk. So without further ado, we will turn it over to Masha. Thanks for joining us.
Thank you very much for having me. This is such a great series. So let me just get started. So today I will tell you about new ideas to look for new ultralight particles. And if something's not working, let me know. So I'm a particle theorist, and in the world of particle theory, we have what we call the standard models, which have been very, very successful. So some of us younger theorists may be too successful because they describe very accurately everything that we see and understand about the fundamental particles and interactions, and also the cosmological standard model, which describes how the universe evolved from its earliest moments to today. And they've been very successful in capturing all of the observations we see, which are quite consistent with the predictions. We have multiple measurements of the subcomponents of the universe, such as gravitational waves. We have dark matter, dark energy, and standard model matter, which all intersect given different parameters and different measurements. We have precision measurements in A, C, and D. And on the particle physics side, we've had great success with both precision measurements, where our predictions with the standard model are accurate out to many, many decimal points, and also with big discoveries of the final piece of the standard model, which is the Higgs boson. However, of course, we all know this is not the full story, and that's what I'll talk about today, is how do we try to fill out these last puzzles. On the cosmological side, we know that there are these things called dark matter and dark energy, just from the gravitational interactions. And on the theory side, we have a lot of questions about why the scales we have are what they are, especially given our understanding of quantum field theory. So, for example, why is the Higgs boson here at the weak scale so much lighter than the Planck scale? What happens at the Planck scale? And maybe slightly less well-known questions, like why is the electric dipole moment of the neutron so small? But this little question here is one of the kind of guiding principles for a lot of my work, which is these three questions here. So on the theory side, there's something called the strong CP problem in the standard model, which I'll describe, that points to new mechanisms that we expect, new particles and interactions. And on the experimental side, we know there's more stuff out there. In particular, we know there should be a new particle or a set of particles that makes up the dark matter of the standard model. And just in general, it will be great to have new windows on trying to look at the highest scales in the theory, because as it stands, we have only explored a fairly narrow range of energies in our experiments on Earth. So to answer these questions, we will talk about the QCD axion and related particles. Oh, sorry, this panel is in the way. Let me just move it. Okay. So the QCD axion, as many of you know, is motivated by the strong CP problem. So the statement of the strong CP problem is that in the standard model of particle physics, we have a lot of interactions that violate charge and parity. So roughly speaking, mirror symmetry. And this is well-known feature of a lot of the interactions that we observe and have been measuring since the 50s. But for some reason, all of this violation does not propagate into the strong sector, so interactions between quarks and gluons. And if you did have charge and parity violation in the strong interactions, you would give the the neutron an electric dipole moment. You can see, for example, that the presence of an electric dipole moment violates parity, because here, let's look at a neutron. You have a spin, mu, and a dipole moment. If you make a transformation under parity, you would flip the dipole moment because it's a vector. So you'd flip it to its negative, whereas the spin is a pseudovector because it's a cross product of two vectors, so it would remain unchanged. So clearly under parity transformation, having the spin, which we know the neutron has, and the dipole moment is not a good symmetry, and the dipole moment was violated. And we go out and measure it, and this has been a tremendous experimental effort for many decades now. And the expected value for the neutron dipole moment, if you just had normal order 1 violation, would be about this number, which looks small, but it's really the size of the neutron times the charge. It's 2 × 10⁻16 e-centimeters, where e is the electron charge. But the experimental upper bound is even smaller, by about 10 orders of magnitude, which implies that this theta parameter, which characterizes how small the violation is about 10 to the -10 or smaller. So far, we only have an upper bound. So if this theta parameter, which is actually a sum of two different fundamental parameters in the theory that come from the gluon sector and the quark sector, is a fixed parameter, this is a huge unexplained cancellation or tuning in the model. And so we'd like to have a better theoretical prediction for it rather than just saying it's a very small number. And luckily for us, there is a great way to explain it, which was proposed almost 50 years ago now, I guess, which is the axion. So instead of saying theta is just a number in the theory, like the electron charge or the or another coupling constant, you promote it to a dynamical field, which we call the axion. So now the axion can have a potential, and that potential can have a potential energy, which is shown here. So if you have some initial value for the axion field A, you have large CP violation, but this potential has a minimum where charge and parity violation do not occur, and being a dynamical field, it likes to relax to the minimum of the potential. And this is a whole that I could go into lots of interesting physics here, so do ask if you have questions at the end. But basically the takeaway from this is just that there's a new particle with this potential, which is set by one high-scale parameter f here, and its mass is inversely proportional to this high-scale parameter, which sets the particle's couplings and interaction scale. So you expect a very light new particle, which interacts very weakly with everything else. And in addition to the QCD axion, people predict that many of these theories, which try to complete the standard model to high scales to include gravity, can also produce many more of these types of light particles, which are similar to this QCD axion. So if you have, for example, theories with extra dimensions, like string theory, you can have zero modes of fields that are propagating in the extra dimensions, which in our 4 dimensions look like new ultralight particles if they remain light after all is said and done. And so in addition to the QCD axion, which solves the strong speed problem, you might expect there to be additional ultralight particles with similar properties that don't necessarily couple to gluons in the same way that this one does. And finally, it was realized that the axion or axion-like particles are excellent candidates to also solve the dark matter puzzle. So although it was proposed to solve this theoretical issue of the strong CP problem, it turns out that the axion's cosmological evolution is also exactly what you would need for cold dark matter of the universe. And for some reason that's not showing up here, I'm sorry, but basically there was supposed to be evolution equation for the axion field, which is basically a damped harmonic oscillator. So what happens is in the early universe, there's some initial condition for the axion value. And then as the universe expands, the friction is given by the Hubble expansion of the universe, which prevents the axion from developing a large gradient. But then once the universe sufficiently expands so the Hubble friction is small compared to the mass, the axion starts to oscillate around its minimum with a equation of state that's exactly that of a cold dark matter candidate. So to summarize, this is the parameter space for axion-like particles. So the QCD axion is this green line here, which I mentioned the axion mass on the x-axis and the axion interaction scale on the y-axis are inversely proportional, so stronger interactions at larger scales. And along this line, you solve a strong CP problem. If you have more general axion-like particles and you take some kind of more or less generic initial conditions in the early universe during a period of inflation, in the blue band, you get order 1 of axion dark matter. So you get the right, you get the right density of dark matter from just having this new particle around in the early universe without having to add any extra model building or other sectors. So these are kind of interesting parts in the parameter space to focus on. And what I want to draw your attention to is that if you have these very light particles, they automatically have very, very high interaction scales. So this FA, which sets its coupling to other particles, is almost as high as the Planck scale, 10 to the 18 or 19 GeV, compared to most particles that we typically interact with, which are much more strongly interacting. So automatically, if you are lucky enough to discover this new particle, it's not just exciting that you found a new particle, but it would also open up a window to these very high scales in the theory. So the summary of why I think it's exciting to look for these new particles is that on one hand, they would address the strong CP problem. They could also make up the dark matter of the universe, and they could also teach us about very high scale physics that is very difficult to probe otherwise. And so how do we look for them? And this is main part of my talk, is how you can use astrophysical probes to look for these light new particles. And this is not a new idea, that some of the best ways we have to look for light weakly coupled particles come from astrophysical objects. For example, if you have something like the sun, and we compare how the sun produces a more strongly coupled particle like the photon or a more weakly coupled particle like the neutrino, you would expect that the flux of photons from the sun is much, much larger than the flux of neutrinos, just because they're produced much more frequently. But the photon is actually so strongly interacting with the interior of the sun that it takes a relatively long time to get out once it's produced. So effectively, you're really emitting photons from the surface of the sun, because any photon that's produced in the volume is going to scatter many times and get reabsorbed and so on. Whereas neutrinos get produced from the whole volume. So even though they're produced much more rarely, and there's also different processes that produce neutrinos, but just order of magnitude speaking, the neutrinos are produced much more rarely, but they're basically produced in the whole volume and they travel outward. And so the flux from the sun and neutrinos is just a couple percent of the whole emission of the solar energy, which is quite large given how weakly coupled the neutrinos are. And this is actually the first place where people were predicting neutrinos to play an important role in solar processes after they were first proposed as a new particle. They were not discovered in the lab until almost 20 years after they were already developed as a key component of solar evolution. So changing the neutrino for an axion, the same thing happens. And these constraints I was showing on the axion plots in gray that I'll come back to are exactly from this type of process, where if you have weakly coupled particles like the axion produced in the core of the sun, they free stream out and they can change the heat transfer and cool the star much more quickly than what we observe. And so this produces a very strong constraint on these types of particles. An even stronger constraint comes from even denser objects like neutron stars that are produced in a supernova. So they are even, the object is so dense that even neutrinos don't free stream out, while axions can. And so by looking at the neutrino flux that comes from a supernova, we can already say that there were not axions that were produced in large enough numbers to change the heat transport of neutrinos out from this neutron star. So these are some of the best constraints we have on these new light particles. You can see here in gray as a premise. So you have constraints from the sun and constraints from supernova 1987A, which exclude all of this parameter space up here. And then of course there are some experiments here, like ADMX, which is at the University of Washington, which are actually starting to probe really significant and interesting parameter space in the laboratory as well, if these particles are the dark matter. And there's lots of ideas about how to keep extending these further. But for this talk, the moral is that you need a lot of energy density to produce, like in a star or in a supernova, to produce a large enough flux of these particles that they can change the dynamics of the object and we can infer that change and either make a discovery or place some constraints. But these are still very far from the interesting parameter space here. And the next kind of densest objects that we have in the universe is a black hole. And of course, that has completely different dynamics than a star or a neutron star, but it turns out that we can still use it to probe these new light particles. And that is that can be done through a process called black hole superradiance. So if you have a rotating black hole, those can produce clouds of very weakly coupled bosons by extracting the black hole's rotational energy and extend our reach in this parameter space to very, very weakly coupled particles. So we'll talk about how black holes can teach us about these particles in two parts parameter space. For axions that interact gravitationally, there'll be one set of signatures, and for axions that interact a bit more strongly, you can still use black holes to test them, but in a slightly different way. And this is a very different production mechanism. Instead of a thermal production of particles, thermal energy of the star being converted to particle production, now we have a rotational energy of the black hole that's being converted to particles, but you still start with this huge amount of energy density that you can use to produce huge amounts of particles. And just to give you a sense of scale, the length scales we will be talking about are Compton wavelengths of these particles, which are kilometers to thousands of kilometers, so very long. And those are set by the size of astrophysical black holes, which are about tens to hundreds of solar masses. Their radii are of the same size, and I'll talk about why that is. So how do we do black hole searches for ultralight axions? Before getting into black hole dynamics, I want to talk about superradiance, which is actually a very simple process. It's the if you have a rotating object with dissipation, you can get superradiance. So, for example, let's start with a rotating or with a non-rotating cylinder with a lot of friction on the outside. If you have a ball that's scattering off the cylinder with a lossy surface, it'll slow down due to friction. However, if you have a rotating cylinder, this ball can actually extract the rotational energy and speed up as it passes by the surface, because at the place where it's interacting with the cylinder is actually going faster than the tangential velocity of the ball, and it'll give it a kick forward. In the frame of the cylinder, basically, it looks like it's slowing down the ball, but in the lab frame, it's actually speeding it up. So if you have dissipation, you can extract energy from rotating objects if they're spinning fast enough. And so this is a quite general kinematic statement, but it turns out to also apply to black holes and wave dynamics. So if you have a wave that's scattering off a rotating object, it can increase in amplitude by extracting the angular momentum and energy of this rotating object. Unlike the ball, here we're not increasing the velocity, but we're increasing the amplitude of the wave. And that's how the energy is growing. And you start with some wave packet and can come out with larger amplitude. And the growth is proportional to the probability of absorption onto the object when it's not rotating. The same as for a cylinder, you need the ball to be efficiently slowed down when the cylinder is at rest, yet to be able to extract the energy when the cylinder is rotating. So black holes are perfect for this because they're perfect absorbers at the horizon. So you have very high rates of dissipation. And you also need rotation. So this gives rise to the superradiance condition. You want the angular velocity of the wave to be slower than the angular velocity of the black hole horizon. So here the energy over the m, I'll be calling the angular momentum number of the wave. So e to the im phi is less than the angular velocity of the horizon. So here's a scattering process of a gravitational wave from a rotating black hole. So incoming is a blue wave and outgoing is a red wave, just so you can separate the two. And you can see that the outgoing wave is much, much larger than the incoming one in amplitude. So this is a full numerical GR simulation that was done by Will East at Perimeter, which shows how efficiently the black hole can give up its energy into this incoming wave of incoming gravitational wave. And that's very exciting, but it's not very interesting kind of macroscopically, because we need to already start with a fairly large wave to be able to extract a lot of energy, and the amplification is proportional to the initial wave that comes in. But it was realized that there can be an even more exciting process, which initially was a thought experiment by Preston Tucholsky called the black hole bomb. So if you have a black hole and you're surrounded by a mirror, particles or waves that are trapped near the black hole will repeat this amplification process continuously. So you start with a wave packet, it gets amplified, it gets reflected back from the mirror, gets amplified again, and eventually the radiation pressure inside the mirror becomes so large that the mirror explodes. This was called the black hole bomb. And of course, this is not a very practical implementation, but it gives rise to the next idea, which is how do we actually realistically trap particles near a black hole? And that can be done just through gravity again itself. So if you have a massive particle whose mass is such that the Compton wavelength is of order the black hole size, then it will have bound states which are localized very close to the black hole. In particular, if you have just 1 over r potential for a black hole, which is g Newton times the black hole mass of the black hole times the mass of the particle over r, then the scale of the gravitational potential is of order of the Compton wavelength of the particle. And if you, so if these scales are comparable, you have most of the particles in bound states that are localized very close to the black hole and can superradiate very efficiently. So this was known for scalar solutions around, massive scalar solutions around black holes in the 70s and 80s. Then it was realized more recently that by these authors down here, that this can actually be used to look for new particles around astrophysical black holes, because the scale of a solar mass black hole is actually what you want for some parts of the parameter space of axion-like particles. So what do these bound states look like? If you're far away from the black hole, it's very simple. We all know how to solve this equation. It's a 1 over r potential, and that gives you energy density of these particles that just follows bound states of the hydrogen atom. So you can classify the solutions by their principal and orbital quantum numbers and L and M. So you can have more angular momentum, which gives more interesting structure and less energy density close to the black hole. So I'll be talking a lot about this parameter alpha, which is the gravitational fine structure constant in analog to the electromagnetic fine structure constant. So it's the coefficient of the 1 over r potential, which is g Newton times the mass of the black hole times the mass of the particle, mu. Or you can think of it as the ratio of the black hole size, Rg, to the Compton wavelength of the particle, 1 over mu. The radius of these bound states is, again, the same scaling as for a hydrogen atom. You have 1 over the coupling times the mass, which is the Bohr radius. And now it's a few to a few hundred black hole radii. So now it's not the same constant everywhere, but depends on the mass of the black hole and to which the particle is binding to. And of course, the important difference is now the occupation number. So axions are bosons, they're spin 0 particles, and you can build up as many of them as you want in these bound states. In fact, they exponentially, these bound states will exponentially grow in number, and we'll see the occupation number can be as high as 10 to the 75 to 10 to the 80 particles. And the other important difference in the solution from what you expect from a hydrogen atom is, of course, that there's a black hole in the middle. And that means that the boundary conditions are very different. So unlike when you solve the hydrogen equations, you say that the wave functions have to be regular at the proton and at infinity. Here we put a absorbing boundary condition at the black hole horizon, because anything that falls onto the horizon is absorbed, and that gives you imaginary frequency in your energies. So instead of just having the energy, which is a mass, minus the binding energy, which is given by alpha squared corrections, just like in hydrogen, you have this imaginary piece, which is exactly the superradiance rate. If it's positive, then these bound states will grow exponentially. If it's negative, they will decay. And whether it's positive or negative is set by the superradiance condition. These bound states are non-relativistic, so the energy is just mass to leading order over this angular momentum quantum number. And just to say, these are, I'm using the language of quantum mechanics for the solution, just because that's where we first see this equation, but these are completely classical states with very large occupation numbers, so you can think of these as classical objects. So how does let's talk about how this would happen in our galaxy, for example. So if new light axions exist, then any fast spinning black hole will superradiate, which means it'll lose energy and angular momentum to exponentially growing bound states of axions. So let's say there's a new particle we haven't discovered yet, like an axion with mass 6 times 10 to the minus 13 eV, very, very light. Then what happens to a black hole with a given spin and mass? So here the mass is on the x-axis in solar masses, and the spin is on the y-axis, where 0 is Schwarzschild and 1 is extremo Kerr. So the blue regions are the superradiance condition regions where the black hole is rotating quickly enough to superradiate into the different levels. So for example, NLM equals 211 is this region, 322 is this region, 433 is this region. And these are the conditions here. So if you have a black hole that's born up here, 40 solar masses and spin 0.9, say in a binary merger at LIGO, then in about a year, if this new particle exists, the black hole will lose a lot of its energy and angular momentum and build up a cloud of these very light particles and saturate the superradiance condition, where now the black hole angular velocity is the same as the phase velocity of the particles and the cloud. So the growth stops. And at this point, the black hole angular momentum has decreased by about 10 to the 78 h bar. So each axion has 1 unit of angular momentum, so L equals 1, and carries away 1 h bar from the black hole. So once there's 10 to the 78 particles, the growth stops. And so that's why we have about 10 to the 78 particles in the cloud. And you also lose a little bit of mass. So this black hole is going a bit to the left, but it's hard to see in this picture because relatively speaking, you're putting a lot of angular momentum far away from the black hole, so you don't need to put that much mass. So what happens to the particles is what I'm showing on the right side here. So the number of axions is shown on the y-axis as a function of time, and the black hole spin is shown again on the y-axis on the bottom panel. So over about 1 year time scale, the number of axions grows exponentially, and then it levels off once the black hole spin is lost. And then on parametrically longer time scales, the next level will grow, as shown in the dashed line here. So now it's 322 level, which has a larger angular momentum, which means it has a larger angular momentum barrier, so it sits further away from the black hole, and it has less efficient absorption onto the horizon, which means the growth rate is parametrically slower. So you can see that the level is going to be growing much longer, about 1 million years in this case, and the black hole spins down again. In between, you see that the number of particles is going down over time, and this is due to gravitational wave emission. So you have a very large energy density in the cloud with time dependence set by the axion mass. So just like you can have a neutron star that's rotating at a certain frequency, emitting gravitational waves if it's not perfectly axially symmetric. There is some energy density in the cloud with time dependence that gives rise to gravitational wave emission. In particle physics language, you can think of this as annihilation. So you have two axions going into one graviton to produce outgoing gravitational wave radiation. And so axions don't have any conserved quantum numbers, and you can just deplete the cloud by radiation. So here is another beautiful simulation by Will East, which is showing a cloud of particles. This is actually spin-1 particles. For technical reasons, they're easier to simulate. Around a black hole in the center, particles are shown in the energy density is shown in purple, and you'll see the gravitational wave radiation emanating out. Because it's this huge classical object that's all rotating together, the gravitational waves that are emitted are coherent and monochromatic, which is a very interesting signal that's quite different from what you've already observed in LIGO mergers. So here you can see that there's a subcomponent of the energy density that's rotating around, and that's what's leading to this gravitational wave emission. So what do these signals look like? Here I'm showing the strain H over time, as seen in the frame of the black hole. So what's the amplitude of the gravitational wave? It's just a very simple cosine at twice the energy of the axion. And then on Earth, you'll observe it in some more complicated form, but this is exactly the same as what people in LIGO and Virgo and growing collaboration across the globe are looking for when they look for, say, neutron stars. As I mentioned, if you have a pulsar that's rotating, we know it's rotating because it's emitting some electromagnetic waves, or we just think there are more pulsars out there that we haven't observed yet directly. They can make gravitational wave radiation, which looks very similar to this if they're not perfectly symmetric. So if they have a bump, for example. And these are the types of searches that are already being run on gravitational wave data, and we can do similar analyses of different classes to try to look for the presence of superradiance in these very light particles. So there's 3 classes of ideas that I think are very exciting, and I'll just quickly mention them here. One is if you do a blind search across the whole sky, and you look at signals from black holes that are in our galaxy. There can be thousands of these signals, as I'll show in a second, and these can be observed and studied in detail if we are lucky enough to see them. So these are just monochromatic lines that you'll see in the spectrum. Because the frequency is set by mostly the mass of the axion, you can also just lump all of these signals together and look for excess stochastic power in a narrow band in the gravitational waves. So you can have a stochastic search, or you can also try to look at known black holes, for example, a merger where you know that the new rapidly spinning black hole was formed, and you can try to see if there's a new signal that's coming from that rapidly spinning black hole after the merger due to this gravitational emission from the superradiant cloud. Now that is a very weak, relatively speaking, signal compared to the merger itself. So for this last one, which would be the most dramatic, you would probably need future generation gravitational wave detectors. But for now, we can do blind searches. So here I'm showing the number of signals we would have expected to detect in existing data that's already on tape that we looked at with these collaborators as a function of axion mass. And the reason why the spread in the number of detectable signals is so large is because we don't know how many rapidly spinning black holes there are nearby in our galaxy. So the range of signals goes from a few to almost a few thousand, depending on what the typical spin distribution is for black holes that are produced from stellar collapse. But for fairly reasonable assumptions, you expect many, many signals. And so once we have hopefully a better understanding of black hole population properties, we can use this to exclude some parts of axion parameter space. If you do see signals, then of course that would be very exciting. You could study them in detail and hopefully convince yourself that you're seeing the product of a new particle. So this is what you can do with gravitational wave searches. And in the last part of my talk, I want to tell you what happens if gravity is not the main driver of these of the evolution of these clouds. And I'm not sure how much time I have left, so someone let me know. But
10 minutes, I think.
Okay, perfect. Thank you. So so far we've assumed that the whole picture is described by only gravity. So you have this new field, which I've been calling the axion, and it extracts energy from rotating black holes. But initially, I motivated this by telling you about particles which interact with the standard model and also have this complicated potential that's generated. So in principle, we expect there to be interactions that are not just gravitational. So we've been focusing on this part down here of the parameter space. The question is what happens once we turn up this interaction? Are there changes to the dynamics? And indeed, there are. And the first thing that turns out to matter is the quartic interaction of these particles. So in addition to the mass term, the potential that's produced will have higher order terms. In the second one usually being a quartic interaction, which scales as the mass squared over this coupling squared. So if you have this quartic interaction, you can get some new, really interesting dynamics in the process that, in addition to what we already discussed. So from superradiance, you have a black hole that produces a cloud of axions, for example, with angular momentum 1. Oops. And you can also have gravitational wave emission, which gravitational waves are sourced by the energy density, which is quadratic in the field. So you have two powers of the axion cloud that contribute to emission of gravitational wave radiation. But now you have a quartic interaction, so you can get these two other processes on the right. So the blue cloud has angular momentum 1, the red cloud has angular momentum 2. If you start with a cloud that has angular momentum 1, you can take two axions and put them together and make an axion with angular momentum 2. But you have some extra energy left over, or negative energy left over, so this particle will fall into the black hole. So you'll have two axions, make one with more angular momentum and one with zero angular momentum that falls into the black hole. You can also have axion emission to infinity. So I have two infinities here. You can take two axions. Once you've built up some number in 322, you can take two axions with angular momentum 2, put one back into 211, and then you have some extra energy left over. So you'll have axions that are being emitted to infinity. So these are unbound particles. So now you have new dynamics for the black hole energy sources, one bound state through superradiance, but then the second level can be populated through self-interactions, and you also carry away some energy to infinity through non-relativistic axion waves. So let's look at that again in this same time evolution picture. So if the axions just interact gravitationally, or if this FA is basically the Planck scale, then what happens is what I showed you before. The number of axions grows exponentially, levels off because you spin down the black hole. They get depleted through gravitational wave radiation. Over some longer time scale, the next level will grow, and the same process will repeat until these time scales become longer than the age of the black hole or the age of the universe. And the black hole spin is basically lost in two big jumps at the end of the growth with each level. And just notice that, here the levels are never occupied, two levels are never occupied at the same time because the growth is parametrically different, the growth time scale. And also, once you start growing a higher level, the black hole loses enough angular momentum that the first level actually becomes not superradiating and falls back into the black hole. So you can see that this level, the occupation number, starts dropping very quickly once the next level starts to grow. The picture changes dramatically once you have a large quartic self-interaction. So you have this new process where now you can exchange energy between levels without talking to the black hole. So now in orange, I'm showing what happens when the FA scale of the axion is much higher, say 10 to the 12 GeV, which gives it a larger quartic self-interaction. So the number of axions will also grow exponentially, but as the first level is growing, it's going to start pumping the next level as it's growing. And so the two levels grow together, and the solid line and the dashed line grow together. And then because you have this process of emission to infinity, you have this way to release energy from the cloud. So as the black hole is pumping up these levels, you're also emitting axion waves out to infinity. And you have this quasi-equilibrium configuration where once you get to a large enough occupation number, the number stays fairly constant over time as the black hole energy is being pumped into the cloud, and the cloud is emitting axion waves. Over a much longer time scale, the black hole eventually spins down, and then you lose the source of energy, and eventually the number of axions will also decrease. So if you have particles with stronger self-interactions, what happens is the number of particles in the cloud is reduced because now you have this energy leak out to infinity. And also the black hole spins down much slower because the rate of extraction of angular momentum is proportional to the number of particles in the cloud. So it's going to be much longer. Now we have this understanding. We can use existing data of black hole spin measurements to place some constraints on particle parameter space. So I told you that you have basically the main thing about superradiance is that it spins down black holes. So if you have a spinning black hole, you can exclude the fact that this process occurred. And since this process happens, it's a classical instability of these black holes. So if you have a rapidly rotating black hole, it'll just automatically superradiate if you have the right particle. So for example, these spin measurements here are from telescope observations of black holes and binaries, and all of these black holes circled in red would be expected to be at the bottom of these blue superradiance curves if there is a new light axion of this mass here. And so we can use the combination of these observations and our understanding of what happens when you have large self-interactions to place some constraints. So here are 5 black holes that we have spin and mass measurements of. And as a function of the axion mass here on the x-axis and the self-interaction on the y-axis, some range of this parameter space is excluded because you would have expected these black holes that have high spins to have spun down to much lower spins than what we observe. And as self-interactions increase, however, we know that the spin down time increases parametrically. So at some point here, you can no longer place an exclusion. And if you remember the parameter space I was showing at the beginning, the QCD axion here falls well into the excluded region, and axion-like particle dark matter is kind of at the edge. So it's still fairly constrained by these spin measurements. And so you might think, okay, well then this is a very gravitational process. We're dealing with black holes. So at some point, once you have no spin down, there's not much else you can probe in this parameter space. But as I said, there is axion wave emission. So there's actually a very cool signature that you can look for in future experiments, which is that you have this very long period of non-relativistic axion emission to infinity. In particular, all of these black holes could still be emitting axions today and sending them out throughout the galaxy. And we do have, so far I haven't assumed anything about how these axions interact with the standard model, but if they do interact, we have experiments that are being designed to look for axion dark matter, which could be in the future reanalyzed to look for these axion waves that are coming from black holes, which would be very exciting. So it's the same idea as for the gravitational wave emission. You have an axion field parameterized by this theta angle that we started with at the beginning, which will be oscillating very small amplitude over time. And if these axions couple to the standard model, you see a flux of axion waves that's constant over millions or billions of years coming from nearby rapidly spinning black holes. And there are experiments that are proposed to look for these. The best ones are ones where the axions couple to spins of particles for reasons that I can talk about if you have questions. So here I'm just showing some projections. So if you have an axion mass, the effect on nuclear spins on Earth is shown on the y-axis. So basically you can characterize it by some effective magnetic field. But the important thing is that these blue regions are all amplitudes of the signal emitted from black holes like Cygnus X1 that I talked about, or other black holes that we think should be out there nearby. And anything above this line would be open parameter space for axion models that so far haven't been probed in kind of the future generation experiments that are looking for axion dark matter. So we could see these axion waves coming from nearby black holes, depending on the details of the axion coupling to the standard model. So that brings me to the end of my talk. So we've talked about ultralight axions and this parameter space here of how you can hope to probe these particles by looking at different objects in the sky. And so we've added to this existing constraints from stars and supernova, we've added black hole constraints where you extract the angular momentum of the black hole. And by measuring spins, you can exclude some parts of axion parameter space. But even more excitingly for the future, you can hope to measure gravitational waves or axion waves that are coming from this parameter space and try to learn about the strong TP problem and the dark matter and these high scales in our universe. So thank you very much for your attention, and I'm happy to take questions.
Thank you very much, Masha, for this wonderful webinar. Let me see if there are questions in the chat. So I see one question in the YouTube channel. Is it possible to constrain the action mass based on the existence of magnetic fields around the superradiant black holes?
Is it possible to constrain axion mass? So there are interactions between the axions and magnetic fields. So there can be some interesting dynamics there. So if you have a very large axion cloud, you could have a conversion from axions to photons in the background of a magnetic field. That's what this experiment, the ADMX, does in the case of dark matter. And you would, in principle, this process might occur, but what we found, and that is something that you could use to constrain or look for axions, but what we found is that the self-interaction processes that I described at the end of my talk are more important for typical values of magnetic fields. So basically, unless you really have very much stronger than expected interactions between the axion and the magnetic field, given its self-interaction, what you would normally do is more efficiently emit axion waves rather than interacting with the magnetic field. Basically, you don't build up enough axions for that process to be important, and first you would lose these axions through self-interactions. But yeah, there could be kind of interesting interactions between the axions and the magnetic field, but they're just turn out to be a bit small to be observable.
Okay, thank you. I think Nicolas Bernal has his hand raised. Yes, Nico, you can unmute yourself.
Okay, thank you. Thank you very much for the nice talk. I could have a couple of questions about this slide. The first one is, here you're assuming that the black hole could absorb axions in this gravitational cloud in the case where you have self-interaction, but the same could happen if there's no self-interaction whatsoever, right?
Yes.
Oh, okay.
Sorry, I'm not sure if I understood your question. So yeah, the black hole can always absorb axions, whether it's being absorbed or emitted or extracting energy depends on the superradiance condition. So sorry, I should have said here that these axions have zero angular momentum. So then the superradiance condition says that they will be absorbed. If you have some other way to mix axions or place axions into a lower angular momentum state without self-interactions, they will also be absorbed. And this can happen, for example, if you have a large gravitational perturbation. This has been studied by some other groups like Daniel Bauman and his collaborators, where if you have, say, a perturbing object, you can have mixing of axions in different levels, and you can have axions produced in anti-rotating levels with angular momentum -1, and those would be absorbed as well. But you'd need very large, basically a tight binary for that to happen. Does that answer your question?
I'm not sure. I'm a bit confused. So for instance, in the lower left diagram that you have, so you have level something, right? So if I understand correctly, you have like two axions, and one of these goes to the black hole, right? It's absorbed.
Yeah.
But, yes, but what about the case where there's no self-interaction? Okay, you cannot have these like 2 to 2 elastic scattering. However, one axion from could get absorbed by the black hole, right? Or not?
No. Yeah, if it's just in 2-1-1, it's not. It doesn't get absorbed. So there is, well, in the very close to the horizon, the wave function is constantly falling onto the black hole. So, but if you look far away, the black hole is actually spinning down, and so the overall energy is growing. So when you just have one axion with no interactions, it doesn't fall. The overall rate is to increase the number of particles. You have to, well, right. So the example that you're thinking of is actually also shown in this diagram on the right. So for example, if you have particles in the 2-1-1 level, but then somehow the black hole spins down below the angular velocity of those particles. For example, if you extract more energy with the next level, then these particles do get absorbed. But they only get absorbed if the black hole is spinning too slowly.
Okay.
Relative to their own angular velocity. So for a given angular velocity, there's some range of black holes where they don't get absorbed, and then there's some range of black hole angular velocities where they do get absorbed.
I see. Thanks.
Yeah.
Okay. I see another 2 questions in the YouTube channel. So the first one is by John Bay. Is the superradiance instabilities only for black holes, or is it possible for neutron stars as well?
Yeah, it's a great question. Excuse me. In principle, as I argued at the beginning, this is a very general process. So it is possible also for neutron stars. The 2 ingredients you need are that the object is rotating and that you have absorption. So for black holes, anything that falls onto the horizon is automatically absorbed. For neutron stars, if you just have axions, you don't have very efficient absorption without assuming further interactions, which can exist, right, between the neutrons and the axions. But once you have those interactions, they're typically better constrained by other experiments or other processes. So it's hard for that to be very efficient. But in principle, there is a rate, and some people have thought about this, and it's just not very large. And also neutron stars can't spin as fast as black holes because they'll just eventually break apart if they spin too quickly. So you can have superradiance from neutron stars, but the rate at which this growth happens will be, instead of tens or millions of years, it'll be longer than the age of the universe. You'll never really see a very interesting cloud around the neutron star, as far as we know.
Okay, thank you. There's another question in the YouTube channel about my academic brother Rohit. He says, nice talk. Can these actions be degenerate with some other environmental effects, such as tidal effects?
Yeah, so I'm not sure if the question is, if you see something, how do you know it's axions and not some environmental effects, or if some environmental effects can mess up the axions, which are both good questions.
Yeah, I think it's more related to the first one, like if you
first one, yeah. The cloud itself can be very much degenerate with other stuff. For example, if you have some cloud of axions or an accretion disk, the cloud is very, however, it's much denser and much more close to the black hole than what you typically expect from other matter around. So I didn't mention this, but we talked about how there are 10 to the 70 or 80 particles in the cloud. But what's that in terms of energy density? It's basically all of that is sitting in a few tens of radii around the black hole. So it's about the energy density of a neutron star that's sitting around the black hole. So that's kind of hard to get another way with just standard model processes. But then if you're doing some specific observation, then it's kind of a case-by-case basis of how you distinguish that from another process, like how good your resolution is on the measurement.
Okay, thank you. Okay, any other question from here? Okay, Diego, you can unmute yourself if you want and ask the question.
I was wondering regarding the recent observation of the black hole of the center of our galaxy, looking at the evolution of this kind of image, something can be inferred about the superradiance.
Yeah, it would be very cool. So what I saw is that they do think that the black hole is rotating, so that's interesting. Yeah, so in principle, yes, this can happen. This process can happen for black holes in the centers of the galaxies, including the black hole in the center of our galaxy. It would be more relevant for particles that have very long wavelengths, because these black holes are much bigger. So this would be for particles that are even lighter than the ones that I talked about. But in principle, the same thing goes through. The issue is that the timescales are all much longer, and black holes in the centers of galaxies are in a sense messier than isolated stellar mass black holes, because kind of by definition, to get to be supermassive black holes, they had to grow through accretion and mergers. So the history of these black holes is much more uncertain. And so if you have these clouds, they could have been disrupted over time and then had to regrow. So having, firm prediction for what you would see is a bit tougher, but in principle, you could have these clouds growing around the black hole in the center of the galaxy. The observation, the Event Horizon Telescope itself is looking very, very close to the horizon. So it's a bit difficult for that to give us information, but you could try to look for other observations like gravitational waves once we have lower frequency detectors or things like that.
Thank you. Okay, see, Nicolas has another question. Please, Nico.
Thanks. I was wondering, what if instead of having astrophysical black holes with a few solar masses, you have a super light primordial black hole and well, not axions but heavy particles?
Yeah, in principle, you could. I mean, this process is kind of, there's one overall scale, which is the mass of the particle, and then there's this dimensionless parameter, which is the ratio of the black hole size to the particle wavelength. So you can just scale it up or down. In principle, you could look at primordial black holes. I think there was even a paper recently about trying to produce new particles from primordial black holes this way. The issue is that, well, we haven't seen any primordial black holes, so then it would be kind of a you wouldn't be able to say anything without making assumptions about the primordial black hole population, but you could do the exercise and see what you get. But absolutely, you could look for heavier bosons or even heavier axions, right? We have a lot of parameter space of axions to go. So you could look for really tiny black holes. In fact, one of the first papers I showed by Detweiler that studied this process, just in kind of, he was a general relativist, so he was just solving the equations around the black hole without thinking about how it would apply to new particles. He has a little sentence at the end of the paper that says, oh, by the way, if you had really tiny primordial black holes, this could happen with pions, which is actually not correct because pions are very strongly interacting. So you'd have all of this kicking in very early on, but in principle, people, and also they decay quickly, but yeah.
Okay, thanks. And also, I mean, all what you say completely applies to any superlight particle, not only axion. I think the only point where you really use the fact that they're axion is when computing the self interaction, right?
Correct. Yes. Well, I also use the fact that they're spin zero. You could also do this for spin one particles, but it has the same qualitative effects, but different quantitative calculations. Yeah, but yeah, it's very general.
Okay, so you could do the same for spin one or spin two.
Yeah,
it would be horrible, I guess.
Yeah, so we did do it for we have studied the spin one case. It's actually kind of fun. Because you have the spin and it's a bit more complicated in terms of the solutions, but you could have like similar bound states, but now you have an angular momentum spin vector. So just like in an atom, you could have like a total angular momentum number and a orbital angular momentum number, and they could be pointing in different directions. So you get more complicated bound states. Yeah. Spin 2 is a little hard because automatically you would have some scale of self-interaction that kicks in typically, or some new states that come in for the theory to be consistent. So then the range where this is valid is fairly narrow because you build up such huge field densities that you're going to start producing other states if there are any interactions involved.
Okay.
Thank you. Okay, I think we're way past the hour. This discussion is also amazing. Thank you, Masha. Thank you, everyone, for tuning
in. Thank you, guys.
in.
Thanks for the great questions.
Yes, our next webinar will be in about 2 weeks. It's going to be by George Wong about the recent EHT image on Sagittarius A star. So stay tuned, and then we hope to see you soon. Masha, thank you very much for this wonderful talk, and then see you around. Bye-bye.
Thanks.
Okay, I think we are not live anymore.